Okay, we're in Chapter 2, Section 2 of Barnett, and our next goals to consider will be being able to transform functions using vertical and horizontal shifts, as well as reflections, stretches, and shrinks. So let's take a look at this. We'll take a look at the vertical shift first. So the graph of y equals f of x plus k can be obtained from the graph of y equals f of x by vertically translating, or shifting, the graph of the latter upward k units if k is positive, and downward absolute value of k units if k is negative. The easiest way to illustrate this is through an example. Say we have some parent function like absolute value of x. That's one of the elementary functions that we just learned. Well, if we wanted to transform this graph, here's two different transformations that represent vertical translation or vertical shifts. The first one is absolute value of x plus 4. Since the value of k here is 4 and it's positive, that means that the graph has been shifted up vertically 4 units, right? So this means vertical shift up by 4 units. On the other hand, if you look at this example, absolute value of x minus 5, because we have a negative 5, then the graph of absolute value of x gets shifted downward absolute value of negative 5 units. In other words, 5 units. What we have here is a vertical shift down by 5 units. Okay? And the best way to see this is obviously to graph these. So here are the three graphs. The parent function in black, y equals absolute value of x. Well, vertically translate this by 4 units. In other words, perform a vertical shift up by 4 units is equivalent to graphing absolute value of x plus 4. Notice all the points of the graph essentially move up 4 units. They all move up by 4 units. Right, so here's a few more. Okay. On the other hand, absolute value of x minus 5, which is graphed below in blue here, that was a vertical shift downward by 5 units. So what happened was, from our parent function, we moved every single point 5 units downward. There was a vertical shift down by 5. Okay, and well, here it is on the other side as well, right? Shift everything down by 5 units. And those are the two different transformations here. Let's talk a little bit about the horizontal shift. Well, the graph of y equals f of x plus h as the input can be obtained from the graph of y equals f of x by horizontally translating or shifting the graph of the latter h units to the left if h is positive. Notice we move to the left if h is positive, and absolute value of h units to the right if h is negative. Okay, very important point to remember. We move to the left if h is positive, to the right if h is negative. Let's take a look at an example again. We'll start with the same parent function, y equals absolute value of x. We usually call this the parent function. The function that you perform any transformation onto, that's called the parent function. Now, I have absolute value of x plus 4, right? So, sticking with function notation, if f of x was absolute value of x, then now I have f of x plus 4, because that would be absolute value of x plus 4. I replace the input x with x plus 4. That's how I get absolute value of x plus 4. Well, notice for this one, what we have to do, because we have a positive h, right? H is positive 4 in this case. This is my h here. Then, h is positive means you move the graph to the left 4 units. So shift left by 4 units. On the other hand, I have absolute value of x minus 5, right? This is what happens when you have x plus negative 5. This is how I will write it in function notation. That gives me x plus negative 5, or just x minus 5 in absolute value. What that means is that now you have h being negative, so you're going to shift to the right. Shift right by 5 units. Okay, and once again, the best way to illustrate this is to actually look at the graphs of these three functions. Here is in black the graph of the parent function y equals absolute value of x. Look at what happened to absolute value of x plus 4. We took all the points of the parent function and shifted them 4 units to the left. 4 units to the left. That's how we obtained the graph of absolute value of x plus 4. Just take them and move them to the left. Okay? That's how that graph was obtained. On the other hand, if you look at absolute value of x minus 5, it was a transition of 5 units to the right. So starting with points on the parent function, move them 5 units to the right. That's how all of these values were obtained. Just shift 5 units to the right. 5 units to the right. Right? So that's how those transformations were accomplished there. Okay, so remember, this is it's a little tricky. When h is positive, you actually move to the left. When h is negative, you actually move to the right. Okay, let's talk about reflection, stretches, and shrinks. It says the graph of y equals a times f of x can be obtained from the graph of y equals f of x by multiplying each ordinate value of the latter by a. Right, so that's what a times f of x means here. Take the values of f of x, the outputs, those y values, multiply each one of them by that constant a, and that's how you get the new graph. It's going to have the same inputs, the same x coordinates, but now the y coordinates will be multiplied by a. And what changes? Well, if a is bigger than 1, this changes the graph, and it results in a vertical stretch. Okay? If a is between 0 and 1, then it results in a vertical shrink of the graph of y equals f of x. If a is negative 1, then it just reflects the graph over the x-axis. Once again, the best thing to do is see an example. We're going to stick to our favorite parent function, y equals absolute value of x, and we'll see what happens when we multiply by different values for a here. So a is positive 2 in the first example, and 2 is a number bigger than 1, so we fall into the second bullet here. So what that means is that the result should be a vertical stretch by a factor of 2. That's what we say. The graph will vertically be stretched by a factor of 2. In the third example, the graph should be vertically shrunk by a factor of 0.5. And finally, we have negative 2x here. Not only are we going to vertically stretch the graph, but we're going to reflect it over the x-axis because this is a negative value. Let's take a look at the graphs to confirm. Here's the parent function, y equals absolute value of x. We have y equals twice absolute value of x, just like we predicted. This is a vertical stretch. Vertical stretch. So compare this to the parent function. We vertically stretch the function by a factor of 2. So for example, well, the best place you could see this, if you look at this point, let's chase points. The coordinates were originally 5, 5 on the parent function. But when I stretch this by a factor of 2, the x stays 5, the y is now 10. It gets multiplied by 2. Likewise over here at negative 5, oops, sorry, this is the wrong value. Here is negative 5. I get moved to positive 10 because at negative 5, 5, multiplying the y coordinate by 2 gives me negative 5, 10. On the other hand, look what happens when we do 0.5 times the absolute value of x, a vertical shrink. What happens is the graph shrinks, and for example, if we chase a point like 4, right, the original coordinates were 4, 4, now the coordinates of the new point are, well, still at 4 on the x-axis, but now we're at 2. So we vertically shrunk by half, by 0.5. Okay, and the last thing I promised you here was the reflection. Here is negative 2 absolute value of x. Not only do we have a vertical stretch of 2, but the graph is now reflected over the x-axis. Okay, and your textbook includes a very nice summary of all these transformations. Feel free to pause the video here to take a look for vertical and horizontal translation. And you could also take a look at this slide. Feel free to pause it again to look at the summary for reflections, stretches, and shrinks.